All good, right? Okay. All right. Very good morning, everyone, and welcome to our fifth session on our bi-weekly webinar series for the civil engineering for the future. And we are excited to have you all today. So it's my absolute pleasure welcoming our esteemed speaker, Dr. Yalin Li. She is an assistant professor at Rutgers University, New Brunswick, New Jersey. Thank you, Dr. Lee, for accepting our invitation and taking time to enlighten us on this evolving topic, the sustainability. It's everywhere, but the true application, how we can expand it, is still yet to be explored. So thank you for taking time to enlighten us uh, on how to advance sustainability in water, energy, infrastructure through integrated experimental research. So to tell briefly about Dr. Lee's impressive academic journey, she received her PhD from Colorado School of Mines, and she has a master's from University of Illinois Urbana-Champaign, and her bachelor's in engineering is from Tongji University, China. So before joining Rutgers, she was at the University of Illinois Urbana-Champaign, so she is not new to or a stranger to Illinois. So she was there as a research scientist at the Institute of Sustainability, Energy and Environment, and also she was part of the Center for Advanced Bioenergy and Bioproduct Innovation. So currently, Dr. Lee is leading multiple federally and state-funded research at the forefront of sustainability. So she explores bioprocess engineering, resource recovery through thermochemical and catalytic technologies, sustainable design, system analysis, and also she explores more on economic, environmental, and social trade-offs in technology development and decision making, especially using the techno-economic analysis, life cycle assessment, and multi-criteria decision analysis. So beyond this research, she is very engaging and very passionate researcher, and she's involved in multiple professional activities, professional associations, journal editorial boards, and also review panels. So I met Dr. Lee when I was doing my PhD at New Mexico State University. Back then, she was in Colorado School of Mines pursuing her PhD. So there was like a kind of a NSF collaborative research where 4 campus work in collaboration. So we had annual gatherings where I had the chance to meet this remarkable researcher. So without taking much time, so let me please join me welcoming Dr. Yalin Li. So Dr. Lee, over to you.
All right, thank you so much. Thank you a lot for this kind of introduction. It was very my pleasure to give this presentation. And then let me share my screen. Hopefully I do everything. Okay. All right. So let me presentation mode. So hope everyone can see my screen. Please let me know and feel free to stop me if there's any technical issues with regard to this presentation. So as Himali just mentioned about, so I did my PhD at Colorado School of Mines, where I met Dr. Himali, and we worked together at this Renew It, which is this NSF-sponsored engineering center to reinvent the nation's urban water infrastructure. And then after I graduated my PhD, I went back to University of Illinois, where my work is more focusing on the bioeconomy and bioprocesses. And now my research, so one part is about doing experiments, as you see on the left side, and then the other part is more looking at the sustainability of different infrastructure systems. So today, since I'm giving this seminar at a civil engineering department, so I will talk more about my projects related to the civil infrastructure part, but then towards the end, I'll mention my different aspects of works on the bioeconomy and some of the resource recovery facilities more related to wastewater treatment. All right, so let's get started. So one figure that I like to show when I talk about civil infrastructures and the importance of sustainability in this sector is this figure, which before I joined Rutgers, before I started working on this these topics, I actually didn't know that. So concrete is one of the leading, concrete sector is one of the leading sectors for this greenhouse gas emissions. One part of the reason is that we use a lot of concrete. So it is the second most consumed substance on Earth, and behind only water. And then it is responsible for about 8 to 9% of annual global anthropogenic carbon dioxide emissions, and then most of that is from cement, which is the key one of the key ingredient of concrete. And then as we are trying to reduce our greenhouse gas emissions in this sector, so there are a lot of legislations or incentives from the federal and state levels to essentially try to incentivize the use of the low carbon emission concrete. So for example, this was embedded in the Inflation Reduction Act that was passed before the current administration. So that was passed in the several years ago, and where it essentially requires the U.S. General Service Administrations to essentially give them a special pot of money and then ask them to spend those monies on infrastructures using the low emissions materials. So here I'm basically essentially showing the tables that sets the limits for what is considered as the low embodied carbon concrete. As you can see on the left side, it's essentially for different strength class of the concrete. It gives sets the limit, the upper limit of the greenhouse gas emissions. And then on the right are essentially the different tables for cement as well as for the concrete masonry units. And then across the U.S., so not just at the federal level, at the state level, there are a lot of bills or legislations that either incentivize or mandate the use of low carbon emission concrete. So for example, so here, this is a map of the U.S. So all the blue states are the states that has adopted similar legislations that includes Washington, Oregon, California, Colorado, Minnesota, New York, New Jersey, and Maryland. And then the green ones are the ones that has either introduced this bill or there are bills under consideration for similar efforts. And this include Illinois, Pennsylvania, Massachusetts, Rhode Island, Connecticut, and Virginia. And then to essentially tell you a little bit more about what those laws can look like. So I'm here giving the examples of New Jersey. So New Jersey passed the two legislations to provide a tax credit to incentivize the procurement of low embodied carbon concrete. So the first one, and this applies for both the corporate business tax and gross income tax. So it's both to the consumers and also to the business. So the first one is this called Public Law 2021, Chapter 278. So it was passed in 2021. So it essentially provides a tax credit of $2 per square meter of unit concrete products if it meets the following requirements. First of all, it has to demonstrate over 50% reduction in greenhouse gas emissions, and then you have to buy more than 100 square feet of that. And then it sets a limit of less than $3,000 for residential properties or $30,000 for commercial properties. And then it cannot exceed your tax liability. So essentially, you cannot get tax refund from the state government if you if you don't pay tax at all. And then it should cost New Jersey is less than $20 million a year. So that was the law for 2021. And then just 2 years ago, in 2023, there was another law that was passed. It provides the credits that's proportional to the amount of concrete reduction. And that is more, the bottom law here is more written for the states, for contractors that works together with the states. So essentially, if you provide some concrete material to the state agencies, such as the Department of Transportation, and then you can claim this tax credit if you provide at least 50 cubic yard. It essentially gives you two types of incentives. The first one is in order to know what is the greenhouse gas emissions of your concrete products, you need to do something. You need to have some document called the Environmental Product Declaration, which I'll touch on later. But essentially, you need to pay some consulting firm some amount of money to get this in the EPD, the Environmental Product Declaration. So the state will be able to reimburse you up to $3,000 to get this document. And then the second part is that the state can provide you tax incentives of less than 5% of the total cost of concrete if it meets the low embodied carbon definition. And then it will give you additional 3% if the production of the concrete involves the use of the carbon capture, utilization, or storage, which is shortened as CCUS. So essentially, when you are producing this concrete material, you capture amount of carbon dioxide, and you meet the requirements for the low embodied carbon concrete materials, and then you will get a maximum of 8%. And of course, this cannot exceed your tax liability, and it should cost New Jersey less than $10 million. However, I want to mention that this is actually can be quite substantial for some large contractors. That's why these type of limits are set. So I talked to some professors in our department who works a lot with the contractors, with the New Jersey Department of Transportation, and they say certain companies, they might provide the state around like 500,000 cubic yard of materials each year. So if they meet both of these credits, this can, like one company alone can essentially exceed this $10 million. So this is like very large scale incentives, and this is why the New Jersey is setting this kind of limit here. And then getting back to Illinois, I did look into the bills introduced as Illinois. It was introduced in 2024, which was last year, to provide these incentives for the carbon utilization, reduction, and removal. However, so the current status is so it's called a session sine, which essentially means like during the past past session, the legislatures did not discuss this bill at all. So essentially right now it's basically introduced, but not really, there's like no vote on this bill. So I'm not sure if this bill will be reintroduced or already discussed at Illinois in the near future. So here, so previously I mentioned this the so-called like low embodied carbon concrete, and then how can we define this? So what is called a low embodied carbon concrete, and then how can we determine like how the emissions associated with the production of the concrete? So we use a method called life cycle assessment. Some of you probably have heard of this. So it essentially is the compilation or the evaluation of the inputs, outputs, and the potential environmental impacts of product systems. So there are two very fundamental frameworks of standards that's published by the International Standard Association, which is the 14040 and 14044. So these two standards essentially sets the method for performing the life cycle assessment of LCA, which includes 4 key steps, which the first one is the goal and scope definition, which essentially you have to set the boundary of system. And the second one is inventory analysis, essentially looking at what inventory you have in your product system. So like what are the inputs and outputs of your system. And the third one is impact assessment. So in this step, use different impact assessment method to determine the environmental impacts associated with the inventory items. And then the final step is the interpretation. So essentially like taking all of this together, and you want to look at the results and to understand what are the implications of these results. And so that was a sort of like a abstract framework. And then a little bit more details here. I mentioned this concept of the environmental product declarations. So these are essentially a way to take the comprehensive life cycle assessment studies and then turn them into the standardized declaration labels for their products. So if you think of like when you buy some food, there are nutrition labels. So these EPDs are essentially the environmental impact labels of certain products. So here on the left, I'm essentially showing the different stages phases that you would incur when you are doing the life cycle assessment. So there could be the product stage, which means you produce something. So if you hear some terms like the cradle to gate analysis, that essentially only includes the product stage, which is from the extraction of the raw materials to the completion of the production of the finished product at the factory gate. So that's why it's called cradle to gate. There's also the construction process, the use stages, and the end of life stages. But for the EPD purpose, it's usually only considered the product stage. And then on the right side, I'm showing the screenshot of some sample EPDs. So here you can see like it essentially needs to include the basic information like the program operator, declaration numbers, the content, etc. So here you can see the content saying the product applicability says it's for the Portland cement, and then there are some context, which means like who performed this analysis, and then on the bottom I'm showing the results, which basically tells you what are the environmental impacts. And you can see there are different categories. So here, not just the global warming potentials or GWP, this is what we usually talk about when we talk about greenhouse gases. There are also other categories like the ozone depletion or smoke formulation. So how many categories you have depends on what life cycle impact assessment method you use. But usually a lot of them include one category related to the greenhouse gas emissions or global warming potentials. And here you can see this is for the for this product. All right, so next. Okay, so one sort of kind of positive trend in this entire concrete industry is that because of the different federal and state level legislations that incentivize the use of low carbon emission concrete, and because you need the EPDs to be able to demonstrate that your product is low carbon. So you can see that after this, the pilot projects pushed by the federal government, there's a significant increase in the amount of EPDs for different types of materials. You can see concrete among the main materials that has a lot of emissions: asphalt, concrete, glass, and steel. Concrete is the industry that has the most amount of EPDs, and that far exceeds other industries. So this, I would think, is a kind of positive part for the concrete business. All right, so I talk a lot about the concrete being a very large part of the greenhouse gas emissions at a global scale. So why does it have like so much emissions? So if you think of what goes into a concrete, so there's the aggregate part, or some people call it a coarse aggregate. There's also the sand, which is the fine aggregate, and then there's the cement, and which serves essentially as the binder to or glues to stay together the different materials, and there's also water. So cement is a main part of the emissions here. And if we think about how we produce cement, we extract the raw material to include the limestones and other oxides, and then there's a calcination process. So if you look at the main ingredient of limestone, which is essentially calcium carbonate, during the calcination process, it gives 1 to 1 molars of the carbon dioxide. And then there's when the temperature is very high, it's 900 degrees C at calcination, and then if you go into the next step, which is the clinkering process, it happens at 1450 degrees C. That is even higher temperature. And both of these steps, in addition to the one-to-one emissions of carbon dioxide from decomposition, there's also the energy consideration of that. So all of that adds up to the majority of the emissions associated with cement, and that's concrete. So there's also some other steps you need to do essentially to get what we call the ordinary Portland cement, which is the most used type of cement, and people usually just call it OPC. So here are some data that we get from the New Jersey Department of Transportation. So they have different contractors, and then each contractor provides them with the EPDs. And then if you look at, so on the figure on the right, essentially the overall column would be the total emissions of certain concrete, and then the blue part are the emissions from cement. So essentially cement accounts for like 80–90% of total emissions for certain concrete type. And then When we are thinking of how we can reduce the amount of emissions in concrete, the first one like low-hanging fruit is actually to use some of the supplementary cementitious materials, or SAMs, that to partially replace cement. So recall that what I talked about, cement is essentially the binder materials in this concrete. So essentially, there's when you harden the concrete, there are like hydration reactions that turn the OPCs into this calcium silicate and hydrates that we call active materials that can bind the aggregate together. So some of the SAM, supplementary cementitious materials, they can also form this binding the active calcium silica and calcium silica hydrates here, so they can be used to partially replace the cement and therefore reducing the total emissions. So the two mostly widely used SAMs at this stage. First one is the granulated blast furnace slags, or GBFS, and people usually just call it slags. So these are sort of waste products or byproducts that's produced from the steel industry. So it is as it's usually a waste, and then there's not too much use of that. So using the slag in the concrete production is actually very beneficial. And the second part is the fly ash, which are the bottom ash products in your coal power plant. So when you burn the coal to generate electricity, and then the bottom ash can be used as a SAM for the in your concrete mix. And then if we look at the EP, so these are essentially the mix formulas we got from some of the contractors from the New Jersey Department of Transportation. So if you look at the greenhouse gas emissions, how that is reduced, a lot of that actually just coming from simply replacing the cement with the SAMs. So here I'm showing two types of concrete here. So they have a comparable compressive strength at 28 days on the left, and on the right you can see it's almost like 9,000 plus psi. And then on the left side, the total greenhouse gas emissions is 432 kilograms carbon dioxide per cubic meter, and then on the right hand side it's only 350. And then the main difference is that here the left side uses 750 pounds of cement per cubic yard, versus on the right it uses almost 200 pounds less. And then it replaced that with the slag, which is shown here. So these changes here essentially leads to the reduction in the greenhouse gas emissions. So that all sounds nice, but if we look at how much of these supplementary cementitious materials we have versus how much of the cement we use, you will quickly realize that the amount of the SAM materials are not sufficient to meet our demands. So here on the top part are essentially the usually considered SAMs. And then here you can see that in comparison with the Portland cement, the quantity just does not add up together. So that's why in some of the studies, they look at filler materials and calcined clays to sort of reduce the overall emissions with the cement, with the concrete, but they also have their own problems and cannot be used as a like 100% replacement of the cement or the SAMs. So that actually leads to the next part, which a lot of researchers and also companies looking at different ways to recycle the waste concrete rubbles. For example, so here are some studies which essentially develop technologies to break the waste concrete rubbles and then turn that into the different part of the materials that can be reused when you are making the new concrete. So for example, so this process, they start with the end of life concrete, and then the first use a jaw crusher and impact crusher to crush the rubbles, and then put that into smaller materials, and then have this router to essentially separate the crushed particles into based on their sizes. So and then here has an air sifter to further break down it into different sizes. So after this process, you will have 3 different parts here. There's this first one, the coarse part, which is of the size at 4 to 12 milliliters, and then this second part is the size less than 4 milliliters, and the finest part would be less than 1 milliliters. So if we compare the purity of the products, you'll see like this coarse products, they call it ADR coarse products. So it can be 90% plus pure, and this can be directly used as the coarse aggregates when you are remaking the concrete. And then the next 2 parts are not that as pure, so that's why they have a further technology to further purify that. And then so essentially they put the medium and the finest parts that's come from the previous process, and then get that into the next part, which further separate and purify that into the fine products and ultra fine products. So what they propose to do is essentially using the end-of-life concrete waste, you have the recycled coarse materials, and you have this further separated fine materials that can be used to replace the fine aggregates, and then you have this ultra fine part that can be used to either as a filler or as a direct replacement of the cement part. So we did some like rough cost estimations of these technologies. So in order for you to recycle like 1 ton of the concrete, so all the cost add up is around like $15 per ton. And then if you think of like how much, so right now, there are concrete recycling facilities, and they charge a tipping fee of around like $10 to $15 per ton for to help you recycle or get rid of your concrete waste. So the tipping fee can pretty much cover this cost of this recycling part, but there's also some economic benefits from this, because we're now using these technologies. You will have the coarse, fine, and ultra fine aggregates that can be reused when you are making new concrete. And then depending on how pure your products can be, so the economic benefits from recycling this part can be 10 to like $70+ per ton. So this essentially means like there are you could essentially benefit economically from using such processes to recycle your concrete. And we also did some calculations related to the greenhouse gas emissions of this process. So if we and then if we use the displacement method for the coarse and fine aggregates, so what we get is that the production of the ultra fine aggregates, which are essentially we think can be used as either filler materials or to replace the cement. So the emissions is around 250 kilogram carbon dioxide per ton, and then compared to that from the ordinary Portland cement, so this is only 30% of the emission. So this, by recycling this material, it also can greatly reduce the greenhouse gas emissions associated with that. So this is one technology is looking at the recycling of the waste concrete. So at Rutgers, we also have additional worked with researchers from material science and also civil engineering on looking at other different processes. For example, here I'm showing the schemes of another process which start with a similar process of the crushing of the concrete rubbles, but they here involve a wet separation using the density to separate the different the concrete, the fine aggregates from the cement, and these are essentially the recycled coarse aggregates, and then the cement fines they recycle from this process. And there's also the hydrothermal vapor synthesis, which is another process they actually use to reactive the recycled waste cement materials. Okay, so and all those are the concrete recycling technologies. But one part that I didn't mention actually has quite some quite some potentials in decarbonizing the concrete materials as essentially just through carbonation process. So as we mentioned about one big part of the emissions associated with the cement, it's essentially from the calcination process where you emit 1-to-1 ratios of carbon dioxide when you start with the limestone, which is essentially calcium carbonate. Which means actually that when you have the cement, you can recarbonate that, so it can get back those carbon dioxide. And a lot of the concrete is in use right now. It will gradually pick up carbon dioxide, but it's just a slow process. So there are researchers who look at the potentials on the different ways we can use carbonation, just the carbonating the existing concrete materials, and look at how much that will be able to, like, what is the decarbonization potential related to that. So here is the figure where they look at the very different carbonation technologies. On the left axis is kind of cut off here, left axis would be the greenhouse gas emissions, and then y-axis would be the cost associated with to carbonating 1 ton of carbon dioxide. You essentially want the technologies that has the low carbon emissions together with the low cost, which is on the bottom left corner. And then there are very different ways they looked at. And then the next table essentially shows you how much you can essentially produce from this process. So they estimate that the total carbon dioxide emissions from the mineral products is around 4.4 gigatons per year. And then just carbonating the cement, just carbonating the end-of-life cement paste, that would be able to offset around 3.4 gigatons per year. And then there are also different processes that you can, like different materials you can carbonate in order to pick up the carbon dioxide. So this this carbonation alone adds up to around like 15% of the total emissions associated with these sectors. So you can see like there are different ways we can reduce the greenhouse gas emissions associated with the concrete. All right, so that basically wraps up my talk associated with the construction of concrete sectors. And next, I want to touch a little bit on the experimental part of my research related to the hydrothermal technologies, and also to talk a little bit on the sustainability analysis we've done for other sectors. So first, I want to give you a very, this is something I like to show when I talk about the hydrothermal technologies. So these are the technology essentially happens at high temperature and pressure. So here I'm showing a phase diagram of water. So on the x-axis, the temperature, y-axis, the pressure. So as you go up in temperature, the pressure also goes up, and then there's a critical point of water. So if you once you go beyond the critical point, you enter the supercritical condition of water. So either in subcritical or in supercritical conditions, the water will have not just water, any materials will actually have very different properties as you observed in your labs. So here I'm gonna try to play a small set of video to show you the supercritical condition of carbon dioxide. So this is carbon dioxide because it is has a relatively lower supercritical condition. You can see once we heat it up, the carbon dioxide will turn into liquid carbon dioxide. And now, once you go beyond the supercritical conditions, you will no longer see the separate phase of liquid carbon dioxide. It's just one phase. And then once you cool it down, it essentially goes back to this liquid phase. And a similar things will happen for water as well. And then even under subcritical conditions, so the water will have unique properties that actually favors the decomposition of the organic materials. That includes the increase in the ion products values, as you can see here. So ambient conditions, water has a KOW of 10 to the negative 14th. But if you go to 300 degrees Celsius, you will have much higher KOW values. KW values. And then it also, the dielectric constant of water will also decrease, which means it becomes a better solvent for the organic materials. And this also helps to accelerate the decomposition of water. And then finally, water is actually an in situ source of the hydrogen. And you can actually use aqueous reforming processes to essentially eliminate the use of the external hydrogen as you are trying to make renewable fuels. Okay, so I'm showing a very busy figures, but don't look at the figure yet. Just take note of the key takeaways. So we looked into using hydrothermal technology to produce the biofuels from algal biomass. So this very busy plot on the left essentially is showing the selling price of the fuels we get from the algal biomass. So on the bottom figure is what's kind of key here, and then this would be the K value. So we modeled a lot of different scenarios for different kind of algae and different kind of technologies. What we arrived on is essentially the lowest selling price of the fuels we can get is like more than $5 per gallon. That is way too expensive. It basically tells you the hydrothermal technologies or HTL hydrothermal liquefaction won't work if you use the freshwater algae. And then we also did some analysis, and this is actually in collaboration with the New Mexico State University. Is we look at what if we use, instead of using the freshwater algae, we use algae growing on wastewater. We also look at different scenarios, and here this figure shows the net revenue, and you obviously want the net revenue of positive values. So after some looking at different scenarios and different seasons of the algae, we essentially shows that there's possibility for to have a net revenue. So freshwater algae might not work for to produce renewable fuels, but wastewater algae might work. So the takeaway here is essentially fuels are actually very cheap. So it's too cheap to justify the use of high quality or costly feedstocks. And then following the research on this, and so next we'll look at, okay, so if we know that the hydrothermal technologies are not very good if we use like very expensive or pure feedstocks, then what waste feedstocks do we have that can be potentially used? So there's a sludge from wastewater treatment facilities, there's the animal manures, there's the food waste, and then there's also the fat oil and grease. So all of these are potential feedstock that we can use to in the hydrothermal processes to produce renewable fuels and also materials. And this is at least one of the projects we are working on, which use the food waste as the food waste and the swine manures as feedstocks. And then after some hydrothermal reactions and also some different separation ways, we actually can upgrade the aqueous products from HTL into the fertilizers. We can produce biofuels that can be directly can be used as a drop-in biofuels. And then also we can produce biobinders that can be used to make the bio asphalt. So the asphalt binders are essentially very similar to the cement binders for the concrete. So asphalt binders for asphalt is the same as the cement binders for concrete. And then on the figures you can show here, these are actually the asphalt we get using the binders from the generated from food waste. Then we also looked at we also performed the techno-economic analysis and life cycle assessments of these processes. So there are different scenarios here, but on the left figure shows you the selling price of the fuel, and on the right, the figure on the right shows the greenhouse gas emissions. So what you can see is that our baseline scenarios and then some scenarios using the electrochemical process to deal with the aqueous products from the HTL, it can arrive a cost that is close to the current cost of the fuels. And then on the right hand, what you can see is that the greenhouse gas emissions associated with these fuels are much lower compared to what we expect for the fossil fuels. And then back to the binders systems we talked about. So my student runs again a different analysis, the different scenarios, and then on the left shows the cost, and you can see the binder cost, the we get right now is even in the negative range. So currently the fossil-based binders usually sells about 10 cents per kilogram, and so this cost will actually be lower compared to the current asphalt binders. And then on the red shows the greenhouse gas emissions, and also in the negative range part. So there's a lot of potentials there. And then, so the next actually a different examples I want to show you the approach we do this TA and LCA is the techno-economic analysis and life cycle assessment. So as you can see from my previous slide is that so when we are doing analysis, we rarely only look at one scenario or one type or one combination of the inputs. So this is very different from the traditional ways of doing the T and LCAs, where you use these process simulators and all the lifecycle assessment tools, and you have very limited ways of doing flexible research. And so you essentially guess maybe like one or two numbers for the greenhouse gas emission and one or two numbers for the cost. But the way we do it is essentially we look at a very different combination of the scenarios and parameter inputs, because our expectation is that given if you are considering multiple technologies, then on the different contexts, the different technologies might be the optimal choice there. And then we will use this to look at the different, and we develop our open source tools to do this TE analysis. On the left-hand side is kind of a web page we developed for the tool called QSDesign, which is for the quantitative system design of sanitation and resource recovery technologies. And on the right-hand side, it's actually a student who did one, like undergrad, who did his summer projects looking at the bioenergy potentials from New Jersey. And here you can see like how much of the products you can get from different counties of New Jersey based on how much of this biomass or waste we have in that different counties. And then these tools like this, because we made it very flexible, so we can actually use that to serve as the digital twins of the processes. Essentially, we can gather like a sensor data from operating of certain facilities, and then to track to model and simulate the process at different stages. So here I'm showing examples where there's a treatment facility in Wisconsin where they have a very, very low phosphorus phosphorus discharge limit, and they implement algae process to reduce the phosphorus levels of that plant. And here you basically can see the gray are the actual sensor measured values, and then the green values the red values are the ones we predict using our models. And then of course there's I talk about I spent quite a few years at Illinois doing work related to the production of the lignin cellulose, biofuels, and bioproducts. And this would be the types of the analysis we do. Is essentially we don't just look at the one point of the results, we look at the entire landscape. So here I'm showing the selling price of the lactic acid, and on the left-hand side, on the x-axis, you see the yield of the fermentation to produce lactic acid from sugar, and then on the y-axis, titer. And then each point here represents one simulation we run that tells you what is the selling price of the lactic acid. So here the shadowed areas, the white shadowed areas are the market range. So essentially, if you go higher titer or higher yield at this like yellowish range, you're essentially beaten market. And then we also can not just do it. So these figures on the left, these are happens at evaluations at a fixed productivity. And then on the right, this GIF shows you like at different. We can also do similar analysis for different productivities at different titer and different yield combinations. And results is showing for the succinic acid, which is another very promising biochemical. And then some of the ongoing research I'm doing now, which is also exciting, is this centers. So this is the PREFIRST. So this is the Center for the Precision Fermentation and Sustainability. So this is a large collaboration that happens between Singapore's National Research Foundation and researchers here in the US. So the main goal is to help Singapore realize their 30 by 30 goal, because you know, like Singapore is a very small nation. They essentially don't really have land for agriculture. So food security is very important for Singapore. So they want to make sure that they will be able to produce nutrition for their own citizens. And because they are in a tropical area, their neighboring countries have a lot of sugar, so they want to develop fermentation technologies to produce proteins and healthy lipids from sugars. And this is what the PREFIRST Center is for. So there's a lot of, so in these centers, there are a lot of synthetic biologists, which essentially using synthetic biology to produce the food ingredients and from sugar, and then formulate that food ingredients into the actual food. So my role in this center is essentially using the sustainability analysis to help them prioritize their research, and also to understand what's the implications. For example, what title they need to reach in order for them to for the produced food ingredient to be market competitive. And that is wraps up my talks here. So my talk today touched on some specific examples related to the concrete production. I talked about so how this sustainability analysis and design can be used to prioritize technology development in a lot of different sectors. And with that, I'm open for questions. Okay, I think we have some time for questions.
Thank you, Dr. Li, for this very broad range. So I'm impressed how you condense everything into this limited time. So I know you are doing a lot of a very wide range of experiments, starting with the carbon reduction in the concrete, and then transition to the thermal chemical processes to generate biofuel and everything. And then you walk us through this useful open source platform where we can do this techno-economic analysis and life cycle assessment. So thank you so much for taking time to enlighten us within this short time through all this data. So thank you again. And if the audience has any questions, please feel free to put that on the chat, or if you can raise your hands and we can unmute and you can ask the question yourself as well.
Yes, sure. So I'll share just because I want to see your face. Because I was sharing my internal windows, I couldn't really say anything. But if you want me to go back to a certain slides, like I can certainly do that as well.
So till the questions popping out. So I have one question. So you mentioned about these platforms. So I mean, they are open source, you mentioned. So do they have like a tutorial where we can walk through and get an idea how these tools are used?
Yes. So let me share my screen again so I can just go there. Okay. So a lot of our bioenergy analysis is on this biostate. So a lot of this, so all the like the tighter yield, productivity related to the minimum selling price, so that is done by BioSteam, which is the biorefinery simulation and TA modules. But we also expand that to include the LC as well. So here you can see there's the user guides here so tutorial to walk you through all the different processes. There are the reference. So essentially this is like the help manual for different modules with this platform. And then there's also this bioindustrial park that includes all of these different biorefinery fields. So that's for the we have, I think, definitely more than 20 bio products at this stage, and all of that are freely open source. So you are free, just use it however you want. And then we also have QSD SAN. And that is more for these applications in the water and wastewater treatment resource recovery facilities. We also have tutorials, APIs, and then we actually also have like office hours and then weekly office hours if you have questions on using these platforms. And this afternoon, actually, we will be having like this week's office hours. So we do have a lot of resources for you to use these platforms.
All right, so that's really helpful because most of these techno-economic analysis tools are not freely available. So having this kind of open source tools will be very helpful. So do we need to have like specific knowledge before using these tools? I mean, do we need to know the coding or any, or are they like
Yeah, I would
user
say,
friendly?
well, I mean, right now the main downside of this platform would be that we don't have a graphic user interface. So all of that happens in coding. So we use Python, which is, I would say, like one of the easiest to learn programming languages. And actually, before I worked on this process, I don't know like any Python at all. So I learned myself. I learned all of this myself. So I think like there's certain barriers on using this if you don't know if you don't have any programming experiences, but I don't think it's very hard to use. And especially if because we already have a lot of units, like unit operations built in the systems. So a lot of those, like you can just directly use and don't have to actually code a certain unit.
Yeah, thank you, Dr. Lee. So do we have any more questions on the chat?
I can
see
say
a hand
Deepak
up.
is asking a question. We can allow him.
Yeah, yeah.
Deepak, go ahead and ask your question.
Thank you, Professor Dr. Tiwari. So am I audible right now?
Yeah, you are.
Yes.
Actually, I'm just writing the chat box, but chat is in my setting. There is not available to write text, so that I can't write.
Yeah,
So
go ahead with the question.
first of all, thank you so much for this insightful session. So I found this presentation very fruitful for me as well. And thank you, Dr. Lee, for this session. So can I get this slide for like details to read what you present right now? And my question is, to my I'm just working in the paper related to the geopolymer concrete, and recently my paper was published in ASC. But and in that we did we explored the geopolymer concrete using machine learning to predict the compressive strength, and we achieve almost accuracy of 90%. That means we are trying to reduce the carbon using geopolymer concrete. So do you think, like, given its environmental benefits regarding reduction of the carbon content, do you think like geopolymer concrete can fully replace our ordinary Portland concrete related to mainstream construction in future?
Yeah, I definitely I would be excited to please also share your publication. I would be excited to read your paper. But I think there's definitely potential on the use of the geopolymers there. So what I have envisioned for the future of this concrete industry is there won't be like one technology that fits all. So because there are certain contexts where like you don't really have easy access to all of the geopolymers or other materials that can be readily used to produce the concrete you want. So what we want is essentially a portfolio of technologies that can be used, where different technologies can be used at different places. So for example, one of the projects that we are trying to do is like in a very remote area where you don't really have any other minerals, but you have a lot of existing infrastructure. And when you are trying to build new projects there, you actually what you want is to be able to use the already existing waste concrete from there. And then there are certain places where you have a lot of access to the slags or the flat edge where you can use in your concrete. So let's say there's no one technology that can be used for all of different contexts, but we want a different portfolio of technologies that can be used at different places.
Thank you so much for addressing my question.
Dr. Himali,
Yeah, we have another question. So could you ask about steel slag? Which process used for ITBOF and EAF steel slag?
I think right now it's used most of that from the BOF slags, but also maybe some EAF slag as well. So I actually recently read a paper where they are essentially combining the steel recycling at the well, they are not just looking at the recycling of the concrete, they are recycling the reinforced concrete, which already has steel there. So using that process, they combine the AF and the other concrete recycling technology together, and then to essentially realize to basically combine these two recycling of the two big emission materials together. So that paper, I think that's is a very interesting read. And then I believe that was a paper based on technologies from either University of Cambridge or Oxford, but it was based in UK. And then there's a startup company that is using trying to further develop this technology as well. Yes. Let me, if you want, let me first. Well, I will send the email. I will send so Himali, I will send you. So I will send my my slides together with the papers I mentioned, so you can distribute to the audience.
Thank you, Dr. Lee. So anyway, we will be sharing this recorded video on our YouTube channel. So anyone who missed or need to watch it again, so they will have that chance. So
That is
Dr.
great.
Mali,
Thank
can
you.
I ask one question?
yeah, go ahead.
Hey, Dr. Lee, thank you for a nice presentation. Good, really nice presentation. In your slide 19, when you presented that during the construction extraction, when you found concrete aggregates, to be honest, you also found some fine material, which you said it processed some cementitious properties. So like, is it compared with the OPC or PPC, or is it just considered as a fine material?
So it depends on what technologies you are using. So some of the technologies, the fine aggregates can be used just as a sand. Some of the ultra fines or like the finest part, some of that are active and can actually be used to directly replace the cement and the slag or other SAMs. But some of that they can actually be used as a filler, which means like they aren't really doing anything; they are just there to occupy the space. In that case, I think you can. Some people have looking at like using different ratios, mixing this recycled part, and then usually like 5 or 10% would be the max you can mix in the actual concrete.
Okay. To follow this question again, like when you say replace as a direct cement, you are saying the complete replacement of the cement, or you are saying the partially replacement of the cement in some proportion?
I think right now, we actually okay. So our there's one professor in our department that actually did some test of the recycled cement materials. So there are some ways we can get a cement that can do a complete replacement with the waste cement. But I also like the way they obtain that with cement. I did the cost analysis. Usually it won't make sense for them. So like technically it's feasible, but like considering the amount of different material we use in that process, it's not very economically promising at this stage. So we're looking at different ways.
Okay, thank you. And one more question, like in your biofuel research, when you said like we can use as asphalt creation, so is it compared with the, like for example, I think you already showed the Marshall stability cubes, if I'm correct, the cylinders which were there. So have you compared the strength part of it? Are they really processing the same values, or is it different?
Yeah, we are testing that. So that is a big caveat actually when I talk about the price of that. So right now, it's working. So based on our last monthly meeting, so our colleagues talk about the testing. So far, some of the testing here already did showed comparable properties, but it's not the full test. So like if you ask me, maybe in like 7 months, we'll be able to know the exact answer. But I would say like so far, the binder actually performed like better than we kind of expected. So like we are very hopeful for this.
Okay. Okay. Thanks, Dr. Lee. Thank you. Thank you so much.
Of course.
Dr. Mali, you are mute.
Yeah, so we don't have any more questions on the chat, so I think we can wind up the session. And again, on behalf of everyone, thank you so much, Dr. Lee, for taking time to share your knowledge and doing this very informative presentation. So since I'm also a little bit into the algae and algal biofuel, so this was really interesting and very useful presentation for me personally. So please join me giving Dr. Lee a virtual applause for this impressive
Thank you so
presentation.
much for
Thank
the
you so
invite.
much.
Thank you, Dr.
Doc-
Lee.
Dr. Tiwari, do you
Okay.
want to announce the next the webinar series? So
Yeah, I can. Thanks again, Dr. Lee. Really nice presentation, informative, and many people are working in recycle construction material, and people are using it because we constructed a lot of construction, and now it's a time like demolition and everything is happening. So how we can utilize this construction, like a already constructed concrete as a recycled material, and people are really working hard in this area because of the carbon footprint and all. So really nice presentation. I'm sure you gave a direction to our people, like what kind of a research they can do using these biofuel. I know many people are using biofuels now. So it's a really a nice area and people will definitely explore it. So thank you so much for joining our webinar series and giving such a insightful presentation and sharing your open source tools which you made it available, because it's really helpful. I mean, we do a lot of research, and if it is not open source, people can't use it. So thank you for sharing all these open source tools details, and our participants will definitely use it. And coming to the next webinar, so for the next webinar, we are inviting Dr. Nikhil Kumar from UC Davis. He is a postdoctoral researcher there, and he is going to talk about the hydrological modelings and air and drought conditions and everything. So I'm sure he is going to enlighten us on a different kind of a research which he is doing. And I'm soon, just after this webinar, is going to post the registration details on LinkedIn. So please feel free to register and join us for the next webinar. Thank you so much.
Yeah.
Thanks, Dr. Lee. Bye-bye.
Thank you a lot.
thank
Thank you
you.
so much for
Thank
the
Bye.
warm
you.
comment.
Bye.